Okay, welcome to the last day. So today we're going to be talking about natural language processing with transformers, and yeah, we're going to start talking a bit about language models in general. Then we're going to see the transformer model, let's say the main parts of the main components of the model, and then afterwards there is a tutorial that we are going to apply. One of these model transformers, we're going to fine tune it for a specific task, and I'm going to do this later. And yeah, it's a bit flexible. I think it's going to be most of the morning we'll be learning about the transformers. Maybe by the end of the morning or in the afternoon, we're going to start with the tutorial. And then at 3 or around 30, there is the visit to the machine room. The ones of you that want to do it, and it's like half an hour or so. And yeah, we should be finishing around 4, I imagine, so you can take your trains to, or I was getting to my train. Okay, so yeah, let's start. Yeah, okay, today, as I mentioned before, so we are going to see now what a language model is, just independent on transformers and model, just, on top of model, just what is it? Then we're going to talk about tokenization. That is an important step in order to be able to feed data to language models. And then, yes, as I said, we're going to learn the main components of the transformer model, and we have some notebooks, and so we're going to be playing a bit with it as well. And yeah, finally, this tutorial here that actually is not BERT, what we're going to fine-tune. We're going to fine-tune a smaller version of this model that's called BERT. So it's a bit faster to train. Anyway, you're going to see it takes a lot of time. Yeah. Okay, yes, a language model is just a model, like the models that you saw before in these days, so you train, and what it's going to do is, given a piece of text, it is going to give you the next word. And giving you the next word, what it means is, like, it will have something like, let's say, a softmax at the end, with many classes of a very large vocabulary. And it will give you the probability that, given a piece of text, the next word is going to be, well, whatever is the name, whatever it gives. Like in this case, we have the cat sat on and then when you pass it to the model, it will give you the list of words, and then you will see like mat, 0.3 probability, rug, 0.2, share, 0.2, and then a list of, I mean, not only possible words, but all the words of a vocabulary that the model will have, okay? And there are two main ways of doing this language modeling, design or training. One is predicting next word, like this one, and another one is called masked language model. That is very similar, but in this case, you give a sentence, and there is a missing piece inside, and the model should predict what is this missing piece. And the main difference is that, if we go back, in this one the model has information only from the beginning of the sentence, or the left of the missing word. And so we call this the context, that is going to use to predict. And in this one, it has information, so the context comes from both sides of the sentence. So the first one is the kind of problems and the training where this is applied is called causal or autoregressive, because you tend to train, like, you pass and then you expect the next word, and then the two words that you have now, you pass them again, and you get the third word, and so on. So this is called autoregressive. And this one is called bidirectional, because the information, the context, come from both sides of the token. It's clear? So any question, please, again, you can just ask. Yeah, okay. So again, the first one is called next token prediction, and this one is called mass language modeling. And these two tasks are the base for the large language models that we see now that we can use in the internet, and like GPT, for instance, because this nowadays the models they have two phases. So they start the first training that they do is called pre-training. Actually, there is no training itself; it's just pre-training. And this pre-training, what is done is in a really like terabytes and terabytes of data, of just text. They are trained to do one of these two tasks: next token prediction or mass language model. And like that, the pre-training is going to let the model start to understand the characteristics of the language. So now it can learn, many features of the language, good enough to create a probability. So you can see the model as a probability distribution that you can pass a text, and based on the kind of language and information, how you've written it, it will give you the next. It can complete it. And actually, you can just repass this one again and complete more and create a full paragraph until it decides to stop. Okay, so this is called pre-training. It's the initial task that the model is trained to do, and then at this point the model only knows how to do this kind of task. Just predict the next or predict something in the middle of the sentence, depending what kind of model is it. And then after that, it's kind of similar to the transfer learning that you saw yesterday, but it's not quite like that. But you can cut the latest layers of the model that are designed for this mask language model. I think I would start saying MLM or next token prediction, and then you replace these layers for something for other tasks, and this is called fine-tuning. And that can be, for instance, okay, I didn't put an example, but it can be like the example that we're going to see today, that is called text extraction or question and answering. It is that there is a paragraph like this, and you give it, and you give, let's say at the end of the paragraph you put a question, and then you train the model to giving that paragraph and that question, it will give you two numbers that are the position here in the string of where the answer starts and the beginning. And so that it would be, for instance, like this paragraph plus the question, how the LMs, the language models, start what is the first start, or how they start their life, and then it can give you, like, from here, I cannot mark, from here to here. And they will tell you from string, whatever, 10 to 100 is the answer. And that one, you cannot do it directly from a pre-trained model, so you need to fine-tune it. Fine-tune is just retrain it and change the last layers. The previous layers is going to be a softmax with all the possibilities, so it will give you a probability of the next word. And this one, you replace it by some, like, it's more like a regression, that you will have two numbers at the end that not continuous, they are so they are integers, but it's not going to be a probability, it's going to be sort of a continuous integer, int. Okay, and so this one you train it for this specific task, and then you can use it for this. And sometimes we can see it in Google, that sometimes we type a question or something and it can give Wikipedia and it's like highlighted, you know? But yeah, and this is this kind of task that, and I think this one is used with a model that's called BERT. This is the one that we're going to use in the afternoon, but in a smaller version. And the pre-training, just to summarize, is done mostly in really large data sets, because the model needs to know enough the language. So afterwards you can you can pre-train it for different tasks. So it needs to have a good, fine-tune for different tasks. It really need to have a very good starting point. And in general, the pre-training is done with specific tasks. Like BERT, for instance, is trained with a mass language model, and after they find, they're happy with the performance, they change tasks. But in general, it's one task or the other one. So they can be two different stages of pre-training, but it's always trained during with the same task. And yeah, the last thing I have mentioned it many times already. This pre-training is, if it is a really large model, it can be very costly. Yeah, it can be very expensive. And so pre-training is done not too often. So it's, let's say, maybe the people from OpenAI, they may train GPT-3, the free one, I don't know, maybe once every few months or once a year. And then, because it's expensive to do, and then fine-tuning is kind of simpler, and because you're starting already from a good point already. And then fine-tuning is similar, as I said, to transfer learning, but in transfer learning you freeze part of the model and you change only some final layers. And here in fine-tuning, the whole model is going to be changed. So you train the whole thing. And it doesn't need as big data sets as pre-training. And yeah, there are many options, like this question and answer that I mentioned. There is machine translation, text classification, any kind of language task that you can imagine. Okay, is it clear? Yeah. And so now I want to introduce you to. We're going to introduce many times to the transformer, but just a quick overview. So this is the schematic representation of the transformer model, and it looks a bit scary at the beginning, but it's not too different to what you have seen these days. And this picture it comes from the paper that introduced that model. That is a famous paper that is called "Attention is All You Need," and we will see why it's called "Attention is All You Need." And it's from 2017. And after that, it really started all this trend and revolution of large language models and this very good performance and capabilities that you can see lately. And so, as you can see, it's clear to read what it has, or yeah. So here you may see many times multi-head attention, here multi-head attention, and here mass multi-head attention. And we're going to go in a bit to the details of what attention is. But this is just an overview. This is one of, I think, the core feature of this language. Same of the CNN, the convolutional neural networks. They have the convolution operators. Is what made them, what distinguished them. In this case, it's the attention, and the attention is something that you can see as when you give a sequence, so a sentence to a paragraph or something to the model, some text. It has some components that they will kind of pay attention to some particular keywords of the sentence, and sort of not ignore but pay less attention to other ones. Which, in other words, it means that it can make more relevant some parts of the text and less relevant other parts. So it can focus and it can use it to extract important features from the text. And this thing appears many times during through the model, and in different flavors. Here you see the first one. So it's a block of this attention, and then a feed-forward network. That is this one you already know what is it. It's just a standard neural net, fully connected 2 layers. But this NX, it means that it is repeated many times. And in BERT, for instance, so BERT is only, it stops here, but it has 12 of these blocks. And another thing that you already know is, so here we put the sentence, some things are done, we will see in a bit. And here you see that there is this connection from here to here, and also this one from here to here. This is like in ResNet, in the residual neural network. This is called a skip connection. This is what happens is, so the point of the input here is saved, and then the attention is calculated, and what comes out of this layer is added to what was before of the layer. And so this is the add, and norm is just normalization. And I can explain you, I will sit down because I cannot see. I will explain you how this works for predicting, for like if you connect to the internet and you work with one of these models. So this is, GPT is not really one of these models. I mean, it's a transformer, but it's different. We're going to see it at the end of the presentation. But so here you see there are 2 inputs, although this one says output. Imagine that you are going to use this for to translate a sentence from, let's say, from English to German. And so here you will put in this side, you will put your sentence, your base sentence in German, and it's going to be transformed in some way that we're going to learn today. But here, after it passes all these transformations, the result of this is going to come to this other side. And we stop here for a second. And here, then the model would put, you don't put anything, the model would put a specific sign, so just a number, that it means start a new sentence. Okay, just start a new sentence. And you have trained it for, or let's say, fine-tune it for machine translation. And so this starting new sentence is going to come and be transformed. And here at this level, you see that it's going to be mixed with your input in English. And then it's going to be transformed. And at the end, this is going to go to a softmax. And based on this part that your input, so that came from this part of the model, and it is going to give here an initial word. This is going to be the first word of your translation, of the translation, and then so it will give you a word, and then this word autoregressively is going to be passed again. This is why it says outputs, because it's going to be passed here again, and it's going to, now you will have initial token, so start token, sorry, I shouldn't, token is, next slide, start sentence, and the first word in German, and then they will come here and interact with the input that you gave, and give another word, and so on, until this softmax give that the high probability word now is end of sentence. It's like the opposite of beginning of sentence. And now your translation is done. And this is one of the ways that these models can be used, in this case for machine translation. But was it clear, the logic behind it, how this operates?
So this is learned word by word, right?
Yeah.
Is it sort of iteration in its written process?
Yeah, something like that.
It learns it and then goes to the next word and then learns it and so on.
Yeah. In this case, I was referring to not to the learning part, but how the model doing predictions. So we put the input in English, and then the model itself put begin sentence, and then the rest was being done with what it was predicting. Is it clear? And so this part in the left is called the encoder of the model. That is going to encode your input sentence and pass it to this side, and this side is a decoder. which to me is a bit misleading, these names, but this is how they're called. And here they are going, let's say, to decode into a final translation based on the input of the encoder, so this side, and based on what is being generated. Okay?
But when does this message passing from the encoder to the decoder occur? Like, why doesn't it occur earlier, but it does? To me, it seems like a bit random when this connection between the left side and right side is.
Yeah, it looks random. Yeah, just please ask questions like that because I semi-understand it now, and it took me hours and hours and hours of reading and YouTube videos to get my head around it. Yeah, but so let's say if you want to think in implementation, imagine that you have some function, or let's say a function that it receives as an input the sentence in the base language, let's say in English. You put it, and it will give you an output. And this output is going to be, let's say, it's the encoder, a set of numbers, some encoded representation of your language that is going to be, of your sentence in that language, that is going to be relevant for the decoder afterwards. And then this one, you leave it there, and you cache it there. And you put it in a variable. And then you have another function that is the decoder. Right? And then in this decoder, when it's not learning, when it's just doing predictions, so used for production, it starts. It has like an input. It has already defined its start sentence. It's just like imagine that you have all the words of the next language, and you also have another word that is start sentence. It's like a keyword that the model understands. So now you pass this one is already created by the model, start sentence, but it also takes as argument the output of your first function of the encoder. And now you forget about the encoder for a second, you put it in a variable, and the same, this encoded representation of your sentence, you're going to use it several times. So you evaluate the model once in the output of the encoder, and you evaluate using the start token. And it will give you one word. This is going to be the output of this side, this other function, that the decoder. And now you evaluated the same function using a start token. Sorry, I want to talk about tokens afterwards, and it's really coming. But a start sentence and the first word that the model gives you, and you also evaluate it in the same output of the decoder, because it's still the same sentence. Okay, the same base sentence, and you use this operation many times, iteratively, as you said, and this kind of iteration is called autoregressive, just because I don't know. I guess it sounds cool, but the idea is that you are reusing the outputs of the same function as input again. Okay. And eventually it will give you end token, end sentence, and you stop there generating. It's not like we saw yesterday and before with the CNNs and the fully connected, that you pass something and then it's going to be a set of operations continue and you get something at the end. In this one, you can see it as you have like two components. You pass something to the first, and then in the second component, you use the output of this first component many times until the translation finishes.
The output, after the output embedding, there's a mask multi-head attention, but as far as I understood, we don't know the end of the sentence yet.
Yeah, that's spoilers. That's going to be later in the. I'm going to talk about it, but I think I want to talk first attention and then mask attention. Okay, but we're going to go back to it. So, is it clear? We're going to come back to this again a few times, probably. Yeah. Okay. Just summarizing this part. This is how one of the ways that this model can work, and the other part is that the crucial feature of the model is the attention. It's a different type of attentions, and it allows the model to give more weight, give more importance to some words in the sentence and ignore some other ones to see what is, to extract relevant information. You can see it very similar to CNNs. That the CNN, when you do this kernel, convolutional kernels, you do it to extract information, and then afterwards this is going to go to just to a multi-layer perceptron, just a fully connected network. But the CNN part is just like learning how to extract, and the other part is more like learning how to memorize from what the CNN for what the convolution extracted. It's very similar here. Okay, just an easy slide. So all these transformers, they mostly come from a library that, well, they come from different papers, but there is this library is called Hugging Face, and Hugging Face implements many of them. So they make it very easily to access all these models, and you can try them yourself at home. And also, Hugging Face has a Hugging Face Hub or something it's called, that there you can post your models, and you can exchange, and you can find models from other people. I don't know if there is some advice on be careful what you download. I don't know if you can download everything from them, if everything is safe, but in any case, there are many options, and you can find safe sources and investigate each of them before downloading it. And it also has three important libraries. That one is called Transformers, that it has all the implementation of the different models, and tokenizers, that we're going to talk right after this about tokenizers, but it's just a way of changing the text into a representation that can be understood by the machine. And datasets. You use just a bunch of datasets, very useful for trying new transformers, and with these three things together, you can really do a lot. And yeah, it's open source and easy to use, and we're going to use it today and in the tutorial. Okay, so now tokenization, as I mentioned before a million times, saying start token. So tokenization is not a part of the model itself. It's some data preparation that one has to do in order to pass the data, the sentences to the model. Okay, so it's not really something related to parameters of the model or anything. And the idea of tokenization is when you give a sequence or a sentence, in this case, the cat sat on the mat, there will be some utilities that are going to divide the sentence in a smaller piece. In this case, we are seeing it was divided by spaces, and it also added, this is a particular tokenizer. There are different types of tokenizers we will see now. And it added these two special tokens that you see they are in quotes as another string. They are just another word. Now this one for the CLS means classification, but it's using the model as this is the beginning of a sentence. Or not a sentence, sorry, of a sequence. It can be a paragraph. It doesn't matter if there are periods inside, but it's the beginning of some text, and sep is the end of the text. So that would be beginning token and end token. And if you use this tokenizer for machine translation, this first token that I was talking about to start the decoded part, it would be CLS. So this is how the translation would start, because when the machine the model sees this one, it knows that what comes rest is the beginning of a sentence. Okay. So this white space, this is a tokenization that we saw now is called white space tokenization, and just splitting the word through white spaces. But this may not be too convenient, because this first, not all languages they have spaces, and but also these tokenizers they just in general they don't. It's not that you give a text and they divide this text in different tokens. So instead, what they have is a vocabulary that just many words, like thousands of words, and they check each of the words inside of the vocabulary, and if it is in the vocabulary, they the tokenizer is going to say, okay, this one is token like here, it's token 1, token 3, token 4, and sometimes if the word is not in the vocabulary, it's going to put a special token, like in general you can see it as UNK, like unknown, and it means that it doesn't know what the meaning of the word, and for hopefully this is a very rare word that it won't appear too much in your sentence, so it shouldn't affect too much your work. But if you divide only by words, then these vocabularies can get really, really long, and somehow we will see later that this will affect the size of the model, and will make the model really long. And also, it will make sequences, when you pass, you convert a text in a sequence, it's going to keep the same size of the sequence, and sometimes you want to shrink it. And what is done, most of the case, is something that is called sub-word tokenization, where the words are divided in small pieces. And I put an example here. So for instance, unexpectedness, which is maybe not a word that appears too common in the text, instead of having in the vocabulary that word, the tokenizer is going to see it, say, in this very text, and it will say, okay, it's not in the word, I'm going to look if I have pieces, and I will make it from other pieces. And here, maybe it has an, because maybe an is a piece that the tokenizer decide that is in the vocabulary because it can be used the same for many other words that it's a common prefix, let's say. Expected is a word, and ness is also a common suffix. So maybe they are 3 of them in the vocabulary, and then in this sub-word tokenization is going to do this. And how these words are, this tokenizer are prepared is you give them again a really long text, and like could be like I don't know, hundreds of thousands of Wikipedia articles, and then so it will this, for instance, a byte pair encoding is going to go through all your text, including spaces, and it's going to check at the first step what combinations, what adjacent 2 characters are common, are more frequent. And then let's say that this UN is not really in English, but and you find that UN is the more frequent, so it will go to the vocabulary where it already has all the words, or all the characters, and it will add to the characters UN. And now it will use all the characters plus UN, this new token, and it will do the same operation. What new tokens are adjacent? What adjacent tokens are more frequent? And during different iterations, it will start finding particular words, because sometimes, like expected, maybe it's a combination of tokens that appears many times, and it will be adding it to the vocabulary. And after many iterations, when you are happy with the size of the vocabulary, like for instance GPT-2, that is a previous version of GPT, uses this very type of tokenizer or at least a variation. It stops, I think it's around 50,000 tokens, and this is a good vocabulary size. In general, it's about this range, tenth of thousand. And at this point, it has so many words good enough to to represent properly the language. Is it clear? And here I mentioned also, so I mentioned byte-pair encoding, but there is a variant of byte-pair encoding that is called byte-level byte-pair encoding, so byte-level BPE, that instead of working with characters, it works with a byte representation of the characters. I won't talk too much about it, but that in the Unicode 8 representation of characters in the computer, there are 256 possible combination of bytes, and it will take the text, look at this combination of bytes, and do the same operation. Find what are the bytes that are adjacent, and just create a tokenization based on these bytes. And one of the good things of this one is that since it is byte represented, you can tokenize many languages at the same time, and without over inflating the vocabulary size. Because if you do it with characters, then you will have like a lot of like a full vocabulary for English, a full vocabulary for you know, for the languages that you have. If you have Japanese, or it would be a lot. So in this case, it's done with the bytes. It's a bit, you have to think a bit about it to understand how it works, but just don't get distracted by it now. But the point is, as a summary, that the tokenizer is going to find, by this algorithm, is going to find different common words and parts and pieces of word, and it's going to use it to decompose a sentence in a smaller in something that you can pass to the model. Okay, and we're going to see now in practice how that can work. And sorry, I'm preparing something for later, and yeah, sorry. So there is, can you see what? Yeah. No. Yeah. It's fine. So this is so tick token until here is the tokenizer used by OpenAI for the GPT models, and it's a type of byte-pair encoding or byte-level byte-pair encoding. So it's a subword tokenizer. And this here, they have this app that is called Tick Tokenizer. I put it in some of the notebooks, so you have the link. And here you can see the amount of tokens, so given this text. And here you see how it divided it. And here we see that it divided, GPT-2 divided in hello, everybody, and some, and also the exclamation mark. Okay, but there are curious things, like for instance, so here we see 3 tokens, but now if we take it and we translate it here, I already have it in Japanese. Hopefully this didn't work. I have no idea. But okay, let's go back. It says hello everyone. It should be fine. Let's say hi guys. Yeah, hi guys. All right. I hope it's not offensive. Okay, it's yeah, it's hi guys. It's the same. We can put actually guys here, and just to have exactly what Google Translate says. Still 3 tokens, and but now when we put the whole thing in Japanese, this is 17 tokens. Sorry, 16 tokens only from this one. So this one was 3 tokens. So let's remove it again. 4 now. Why? No, because I have a new line. Okay. Okay, I see that there. So this one is 3 tokens. And the same thing in Japanese is, I have space. I don't know if there is something, but it's many tokens. So here we have more than twice the amount of tokens. And sometimes we hear that that languages that are not English, they don't do very well for machine translation and for this kind of NLP, natural language processing tasks, because there is not enough text in the same in these languages. So there is more training done in English because a big part of the internet is in English. But this is one component that is important. But another component is that the tokenizers, at least right now, they don't work the same for all languages. And in English, you can pass to this model a very large text. And these models, they have, as you mentioned, these models, they have a certain maximum sequence length that they can receive, they can process. So you can pass and you can train as a result in English in very large amount of text at once, while in other languages like Japanese that have a different alphabet, you will constrained by smaller sequences, because when you tokenize something like in Japanese, you will use a lot of space of the sequence length that the model can process in a small, in a smaller amount of information. Is it clear? It's not clear, but I don't understand. Questions? No. We have time, we can discuss if... Okay. Okay. So here, all right. Another curious thing, just this, by the way, this idea of showing this, I learned it just last week in a video of this guy on YouTube. I put the link also in one of the notebooks, so you have it. And he has like 2 hours and a half presentation about tokenization only. It's really an important topic, and you can watch it afterwards. It's really interesting. And he showed something else pretty cool. That is, so he showed a Python example. So you know that these models, you can use ChatGPT to give you Python scripts, and so this is well indented. It's just if I put this, it's just like it is to. I think I can make bigger the screen. Okay. So in Python there is the indentation that is an important part of the code. It's not optional. And here, if we tokenize it with the tokenizer for GPT-2, we see that it has this piece of code has 309 tokens. So this thing here is what you're going to give afterwards to the model for training and for predicting or whatever. And you see here that the spaces, each space is a token, and this here is one token itself, including the space before. But there is a lot of tokens lost in single spaces. And if we look at the tokenizer instead of GPT-2 of the GPT-4, which is this one CL 100K base. Now it reduced from 309, so if you didn't pay attention. So before was 309 tokens for this Python code. And it reduced it to 180. And this is because they increased the vocabulary size. And now they have tokens that are multiple spaces. And you see now this whole this space here now is a single token, as you see, one color, while before with GPT-2 it was one token per space. And thanks to that, GPT-4 does much better with Python code than GPT-2, similar to what happened with the language, because it can be trained in bigger chunks of Python code that GPT-2 couldn't, because it lost too many spaces too many tokens, sequence length, let's say, in white spaces. Okay, is it clear? Yeah, this is a very good, interesting example. Okay, so we can talk a bit more about tokens. Okay, yeah. Why tokenization? Again, as a summary, it well, first is you cannot pass just strings to the model. You need to pass some sort of numerical representation of the sentence, and it also, thanks to the subdivision of words, it improves when there are rare words, because like unexpectedness, that is, it could be very rare, maybe in a subword tokenization, if you don't want to have very large, really long vocabularies, maybe you will have to ignore words like unexpectedness. But here, in this case, we can somehow include it keep them included in the text, and it can be adaptable to different languages, because things like languages without spaces, or languages that when you conjugate the root of the word, they changes a lot. That one with like passing word by word, it would, and again, take a lot of space of the sentence size, and like that it is possible to adapt to these languages and reduce it. And finally, it's nothing why tokenization, but this is a very, choosing the tokenizer and building it for the different languages is very important, because all languages, they have different characteristics, and they can be, the way they work, it can be completely different, even if they have the same like basic grammar rules and conjugations and things like that. But the way that the words are changed and modified with where they are in the sentence, or how they are used, and the conjugations, it's really to have it's very important to have a tokenizer that captures well, understands the language. And yeah, in NLP there is so there is a component of the machine learning side, but there is a very important component of understanding the language and knowing exactly, being able to tell if the way you're representing it makes sense or not. And so now we can go to the slides, and sorry, to the notebooks. And maybe I updated something this morning, so maybe you need to do git pull in the repository. Thanks, Rocco, for the links. So git pull, and there is a directory called transformers, and we can go now to the notebook 1 tokenizers. Sorry, it's really small. Is everybody there already? 1. This is one inside of transformer 1 tokenizers. No. So this one, I just wanted to show you very quickly. Just first a small introduction to the Hugging Face library, and just to you see how the tokenizer works in practice. Not how it works, I mean how you use it. And so we're going to use these transformers are part of Hugging Face, and it so Hugging Face has many checkpoints for different models. So it's just the weights stored that you can download them and use it in your model. So they are pre-trained models, and so you have these different possibilities of models, and you can use not only the implementations but also their weights. And here we're going to use a weight that is called BERT base uncased. That is for a transformer model that's called BERT, and uncased means that it takes only uncased, so there are no upper cases, everything's uncased in the text. And a very important thing with the tokenizers is that when a model has been pre-trained with a particular tokenizer, if you're going to use it afterwards for fine-tuning or for production or whatever you want to use it, you have to make sure that you're using the same tokenizer. And and they do something very convenient, that is, in their checkpoints, they also write which tokenizer they use. And they have this utility called auto-tokenizer. And then you can do auto-tokenizer from pre-train, and it will give you the tokenizer that this pre-trained model was used for. Okay? And so if we put here tokenizer, this is called BERT tokenizer fast, and it's of a type of tokenizer that is called word piece, and it's a subword tokenizer. And so you see here that it has many, this one we saw already, SEP and CLS, so beginning and end of sentence. It has unknown for the unknown words that appear that are not in the vocabulary. And yeah. So, and here you can see, for instance, the vocabulary size. I don't know if I put, yeah. These tokenizers, they have vocabulary size. And this one, so this means that it has 30,500 words. And you also can see the vocabulary. The vocabulary is just a bunch of pieces of words and words. And they have a number assigned to it. And using these pieces of word, when you give a sentence, we close here, such as let's tokenize something, it will divide it in pieces. Here we see the pieces. It will divide it in pieces that correspond to entries in the vocabulary. And here we see, like, for instance, tokenize, that is not a common word, or at least it didn't used to be. It was divided by token and ice, and this word piece used this symbol of this sharp to specify words that tokens that they are not a full word in English, but a part of a word. And then you see here CLS and SEP as beginning and then tokens. So the main things that you use is mostly encode. That encode it will give you the numbers directly, and I think there is also decode, but I don't remember now what you pass. So the code would be the opposite. Let's see. No. Yeah. The code, it will give you back the sentence. So here I put a star to pass every token independently. And convert IDS. IDS is these IDs, the numbers to tokens. So it gives you the corresponding actual token in the vocabulary. This is very simple, and so the rest of the notebooks, we're going to be starting with this one, and we're going to be building on it as we go through the transformer architecture. Okay? Would you like 5 minutes to play with this, or is it simple? Okay, you have 5 minutes to play with it. So here, if you can find if you go to the Hugging Face page, you can find different checkpoints, and you can use the same structure of this notebook, and you can instead of BERT, you can use another one. I used OpenAI GPT in this case, and use the same auto tokenizer, so it will give you the tokenizer. Now, if you do, let me see that tokenizer. here. It will be the OpenAI GPT tokenizer first. And this one has a different 10,000 more words. And here, when you see the tokens, it looks completely different because it has a different vocabulary and it tokenizes in a different way. So it's very important that so you use this from pre-trained tokenizer and always use the same tokenizer that the model was used. So the checkpoints that you're getting, the model was used to in the pre-train. Okay. Okay, so it was clear? Any questions, general questions about tokenization? Okay, yeah, I think we can continue to the next part. And now, so remember, so tokenization is the construction of the vocabulary. If in general, we don't make tokenizers. Some people make tokenizers, and we are users of the tokenizers. And the construction of the vocabulary is called training the tokenizer. This is just finding this pairs of words and recursively, and to build a whole vocabulary. And once for training, this vocabulary is kept fixed and is not touched, and it's not a parameter of the model. It's just the way you pass the data to the model. Okay, and so. The next, now we're going to go through the different steps, the different parts of the transformer model, and now these inputs. Now we know that they are tokenizers, so they are tokens. And the first thing that we see here is input embedding, and we're going to see what happens there. So the tokens now, so they are numbers, and they can be passed to the machine knows you can pass numbers. But if you have tokens that are similar or they are different, these numbers are randomly assigned. And even if they were not, it's just with a single number, it's very hard to give meaning to the relations between the words. You know, like if king is 25 and queen is 10,000, this subtraction doesn't mean anything. And to give some meaning to the words, these tokens are replaced by a set of vectors. So every token, we have a vector assigned to it. And now these vectors are of high dimensionality. For instance, in BERT, the dimension of these vectors are 784. And they are called word embeddings. And how it works is, so you have the sentence from the text. You use a tokenizer, and you get a representation in tokens, as numbers. And now you have an embedding table, and this embedding table is part of the model. This is just a matrix of vocabulary size. So imagine just one vector per each of the tokens, so vocabulary size, by dimension of the embedding vectors. And what is going to happen is that when you give this sequence of tokens, there will be a lookup table that will find the tokens in this matrix, in this table of embeddings, and it's going to replace the sequence to just two vectors. And now we have a representation of words that it can have some sense. Now, if these tokens, these embeddings, we manage to organize them, we can have vectors that are similar, words that are similar, and they can be in a similar part of this high-dimensional space, and vectors that are, words that are different, that they are not too related, and they can be in different parts. And now there is a meaning when you do operation with words, and now you can do like similarity and things like that. And I forgot. So this one is the first thing that's going to happen in the model. So this is a lookup table, and these embedding vectors, these embedding values, they are parameters of the model. These are the first parameters that we have seen now, and they are initialized random. And during training, they are adjusted. So the model during the training, the training is going to find what are the proper values for these vectors, and they are going to get organized. There are different ways of doing word embeddings, and there are word embeddings that they are for different problems, and they predate the transformer. And some they are just trained by by like kind of minimizing the by looking for similarities in text. Like you have a matrix like this, and you use a lookup, and then you put a very simple neural network that it will give, like, let's say if two words are continuous or not, and you can train something like that. And there are many examples of word embeddings, but in the transformer model, they are part of the model, and the training finds what is best what is the best way to organize them. Yeah.
So the dimensionality of that vector space is the hyperparameter?
Yeah. So it's a hyperparameter, and it's in general it's high. It has to be a high dimensionality. Again, 784 for BERT, and yeah. So they say there is, or I just yeah. There is something in language that I just heard for the first time preparing this course. It's called distributional hypothesis. That is like, it's pretty much what happens with these vectors. They say something like words that are they have similar meanings. They appear in similar contexts, and this is pretty much what happens with embeddings. So we can have like groups of words, and there is a notebook, the number 2, the same directory. It's called 2 embeddings, and again we're going to have a look to Hugging Face. And now we introduced. So I'm trying to give you some Hugging Face tips, and at the same time with this, so 2 things at the same time. I'm sorry, but now we introduced two new things: autoconfig, and that it is going to give you all the parameters, the hyperparameters with which the pre-trained model was set up. And BERT for pre-training, this is the model now. Before we only look at the tokenizer. Now we're going to see the model as well, because the embeddings are part of the model and tokenizers are not. So we get them like this: tokenizer from auto-tokenizer, from here, model. We know the model, and we pass the checkpoints for that model. And config from autoconfig gets the configuration. So if we look quickly to the config, it's a bunch of parameters, and this hidden size here. Sorry, I gave you a fake number. Is 768, not 48. And this hidden size is going to be the same of the dimensionality of the word embeddings. Okay, I can close this or not. Yeah. So let's start with the same sentence as before. Let's tokenize something. Encodings. We see the tokens here, and we're going to use it to pass to the embeddings to see how it works. And here we print the model for the first time today. And so this is pretty much the same that you saw in all these days with the CNNs, that PyTorch gives you a printed summary of all the layers. Here, don't get to I don't know, a stock in the indentation. There are things that I don't get very well why they are indented, but in general, you see there are different layers as you go down. And here we see inside of the model there is this part called embeddings, in particular word embeddings, and there is this matrix here. Sorry, this is not the matrix, it's a class, but it has this lookup table inside, is what it's going to do. Here is the vocabulary size. Just remember from the tokenizer, vocab size 35022, so it's one vector per token, and 768 we see it in the config.hidden size. I don't know, 768. And so if we do, so we can go inside through this parenthesis, vert.embeddings. We get there are different embeddings, but we're going to focus only in this one now. And we have, word embeddings. Is the matrix, and you remember this weight parameter of the layers in PyTorch. This is the lookup table, okay? Which is vocab size by embedding dimensionality. I put them here, the same. So if we apply these word embeddings to the encoding is the list of numbers that are going to be applied to the lookup table. Now we get, so this is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we get the same. So 1 is the batch size. 9 tokens, it will be 9 vectors of 768. Okay? So now we did effectively this. We started with the string text. We converted it in tokens. And with this token IDs, we use it in the lookup table of the embedding table, and we get the sentence represented as a list of vectors. And now every token, so every word, it has something that thanks to that we train and they adjust during training, they have some meaning. And there will be words that are close, words that are far, and words that are going to be similar, words that are going to be unrelated. And we can do a simple example here. Let's get the word queen, and we tokenize it. So we get the token for queen, and then we apply it to the embedding table, and it will give you the embedding for the word queen. And we're going to do the same for the word king. And then we can compute a similarity measure between them. In this case, we're going to use the cosine similarity that is defined like this. It's the dot product between the two words, the two vectors, king and queen. And if the dot product is perpendicular, it will mean that they are unrelated. It's going to give 0. And if they are one on top of the other one, and you normalize it, it's going to give you 1. So from 0 to 1, you can get the similarity. And in this case, we get this number 65, that I can tell you that is high. And we can compare it, for instance, let's put a computer here. It's a bit silly exercise, but it can be. And the computer and king, they are not too related. And we come back to queen. Maybe if we put man and queen, man and king are not too related. And we can try. I mean, this is really, it's not for humans to understand that this is for the model, okay? We are just overdoing it here. Let's put banana and king. Banana and king, I think, are more related than computer and king. Apple. So maybe fruits are a bit higher. And this is the idea. I hope it illustrates it in a. I don't know, at least a bit. But now with these vectors, the model can see similarity and can find some meaning between two different words that with tokens alone, it's not possible to do. Was it clear? Yeah.
When we go from the token to the vector,
yeah.
How do we go? How is this operation done? Is it like randomly initialized and then it's the result of a training, or is there an algorithm that maps the token to the vector?
No. The token is a number, like in this case. So you have these numbers, and then the vectors are. Okay, I understand what you mean now. No? So you have this. You have all the numbers in the vocabulary, and you have all the tokens in the same size. And I think it's a good question. I'm trying to think and talk at the same time, but I think you can see it. I think it's easy to understand it after it's trained. You will have a lookup table that the token 0 is going to be the 0 in the first vector in the matrix. The token number 1 is going to be the first column, the second one, the column 1 in the matrix, and so on. So there will be always a correspondence. It's just like indexing. Like anytime you pass the token n, it will go to the column n of the matrix. So there is no mixing. So it's always the same.
What I mean is, how do we know when the vectors are related? Like, how do we learn that king is more related to...
Yes. This is during training. It starts random, and then during training, the model starts seeing different sentences, mostly just the pre-training phase, and then all these numbers, all these vectors, they are parameters of the model, and they are going to be adjusted. And at the end of the training, this thing it will have some meaning for the model. Yeah. Okay, so this one I think is very simple. It's just a lookup table. I think this notebook maybe we can skip. Okay. So we did. Again, we started with a sentence. We make it tokens, numbers, and we replace these tokens by vectors. And these vectors, the value of the vector, they are found out during training. Okay, the model is going to find what these vectors they have to be, what the relationship between the vectors have to be, so it produces a good language model. That's it. And the next, if we go back here, we're going to skip for now positional encoding. But the next thing that we come here is the multi-head attention. And as I said before, attention is the crucial part of the transformer, and we can see it more as extracting information from the text and not like memorizing. It's similar to the convolutional kernels that they extract information from the images. And let's say that we have these two sentences. The first one is time flies like an arrow, and the second one, fruit flies like banana. And here we have the same word twice, but they have completely different meanings. And this meaning is, we know that they have different meanings because of the context where they are. However, the embeddings, as we have one vector for this one vector for this one, and so on. So they are independent, and so far there is no information that can tell the model which flies is this one, the fruit flies, or the verb. And this is how this is managed in the transformer model, is through something called attention. And the idea is that to create contextual representation of every word. So the idea of the attention is to give to fly here, to the embedding of fly, to give them some information from the rest of the sentence, so the model later on can know that this is the fruit fly and not that the fruit is flying. This can be done at this point only by just mixing the embeddings. And what it means is, like, for instance, if you focus on flies, when the sequence arrives goes through the attention block in the transformer, this flies, for instance, is going to get information from fruits, from like, and from banana. And but this information is not just going to be just to add the tokens, because if you add all the tokens, then if you do the same from fruit, flies, like, banana, all the tokens are going to be the same. So you have the sum of all the embeddings, then the sum of all the embeddings, the sum of all the embeddings. Instead, what is happening is the other part that I mentioned before, that is like giving weights to different, giving importance to different parts of the text. And in this case, if we go to fruit, we start with the first embedding in the sequence. We look to the rest of the sentence and we say, okay, this fruit, to what is similar, or what words in this sentence are related to this word that can be that can give that we can use these words, these particular words that are more relevant for fruit, which word we can add to this to the embedding of fruit, so we can give information of where the word fruit is in the sentence. Like, it's not isolated; it's in some context. And like, for instance, maybe fruit is not easy to see, but again, this is not for humans. This is for the machine to understand. But let's say for flies, what makes the give the information on more for us humans more relevant in this sentence is that the word fruit next to it and the word banana, which is fruit, probably these two, they give the same amount of information, and like, so the fact that there is like banana. So maybe we can take to the embedding of fruit and add a bit of of flies, and add a bit of fruit, and some of like, and some of banana in different degree, and same for each of them. Maybe like is more important that flies is before, and maybe fruit is not important. So maybe we can add to give information of the context to the embedding of like more of fruit, so more of flies, a bit of fruit, some of banana. And now the token, if we add these tokens with different weights, now before that we have embedding, fruit embedding, fly embedding, and so on. Now after we do this process, each of the embeddings are going to be replaced by some combination of the rest of the sentence. Is it clear, or I have been rambling for like? Is it clear? Okay. So summary, we want to find a way to give to the embeddings information on of the context where the embedding is, and this is done by adding the other embeddings to it, but with different weights. If the words are very similar, they're related. We add it with let's say if you have a 0.0 to 1 weight to it, with something closer to 1. But if the word is completely unrelated, maybe we don't add too much. Like, let's say here this says fruit flies like banana, and TensorFlow is a package. Maybe all the rest of TensorFlow is not really too relevant, so it will be added with very low weight to the fruit flies, to the fruit. Okay, and this in practice, this is done by if this is the sequence as embeddings. This is done by taking each of these vectors, let's say the one, and getting a weighted average of the rest, and replacing it by it, and same for the two, all of them. Now all of these embeddings, they have been replaced by weighted average of the context of the rest of the sentence. Okay, and this weighted weights here, AII, they are called attention weights because you can see it, the names come from each word to which other words are going to attend. They're going to pay attention to. And this one can be, in general, is calculated as a similarity function between the two embeddings that are being added. And that can be, for instance, a dot product, as we saw before with the similarity, cosine similarity. But most common is a dot product with a softmax to it. So they are a scale between 0 and 1, and they all sum 1, like if they were probabilities. Okay? So this is a basic attention. And attention also predates the transformer, and it used to be used in recurrent neural networks, in some recurrent neural networks because in recurrent neural networks, just is autoregressive. You give one word, but during the training, you give one word, then the next, and every time you get gradients. And sometimes when you have very long sentences, the some of the embeddings would get like they would get very really small and tiny, and they would enhance them by multiplying some attention weights, so that they are not forgotten if the sentence is too large. So this is the basic of attentions, and in the transformer model, this is not calculated precisely like that, but it's pretty much the same. This softmax in the transformer model, so the softmax of the dot product, what happens is that the dot product between all the pairs of tokens is projected to a different space with two matrices, but you see, it's the same operation. At the end, it's a similarity, and they are scaled by this decay. They call it the dimension of this matrix, and this a projection here occurs to a smaller space. So and afterwards, this one here, the weighted average, again the vectors are also going to be projected, and this one is also smaller space, and this E, now they are going to become a smaller dimension than the original embeddings. Okay, and in the transformer model, this W matrices, they are parameters of the model, and they are found out during training. And the idea is that with different Ws, the model can pay attention to different things, can like find different. Pay more attention maybe to the grammar, or maybe to the grammar is everything, I guess, but to the kind of word, to how the words appear in the order of the sentence, or maybe some look more to the gender of the sentence. If we talk about of a woman and it says she, to realize that it's the same person that's talking about, and things like that. And these matrices, these parameters of the model are this one. This projection is called query, this one is called key, and this one is called value. And these names, they come from working with databases, and I don't know very well the story, but it comes from something that has to do with looking for similarities to query inside of the database, like Google or so, when you type for a question and it's looking for an answer, okay? But the important thing is, it's pretty much the same, just a similarity, and just a weighted average. And now after attention, there is the embeddings, they have contextual information within them. And so this is called a scale.product attention. The scale is because of this part. And so remember, I said that this they get smaller. In practice, in the transformer model, it's the last bit about attention, is that this operation for a single input, for every input, they are done multiple times at the same time, and with different Ws. For instance, in the BERT model, there are 12 of these vectors are computed, and they are smaller. And the idea now is that by doing 12 different computations with 12 set of W matrices, then these Ws, they are going to evolve during the training in a way that they will pay attention to different things. And they are called attention heads, and the whole thing is called multi-head attention. And the idea is that maybe one head is going to pay attention to this gender thing that I said, or another one is going to look to specific words, that how they appear one after the other one, another one to if it's plural or singular, this kind of effects. And since they are smaller, afterwards they are all these are concatenated in the direction of the dimension of the embedding, and so keeping here the same sequence length. So after the attention, you get again a vector of the same size of the original sequence that you passed, but they will have by chunks like contextual representations, but all of them may be different, looking to different things. And like like the DNA, that they have like different parts that mean different things. It's something like that. And at this point, so now we are here after the attention. The model has learned to extract information by looking to different parts of the sentence and looking the words where they are from the text that we gave. Is it clear? Okay, this maybe let's not get too much worried about the details and the math and the concatenations, but the summary is that at the end we get a representation of the sequence. It's the same length. Now, for us it becomes a bit strange, but every embedding vector has information not only of itself, of its token, but also where it is on the sentence. Yeah, and we do it comes from this multi-head attention thing. And yeah, afterwards, this one is an easy one. So afterwards, there is a skip connection here. So this is not past continuum. Instead, this vector, this sequence of embeddings is added to the original embeddings, to the non-contextual ones in this skip connection, and there is a normalization, and then it continues to a feed-forward network. And the feed-forward network is what you know from the other day, multi-layer perceptron, and in general it is designed as 2 layers. It is a layer that is going to increase the dimension of the input. Then there is a YELU activation function that is very similar to the ReLU, but I think it has something like this down, and then it goes up. And then there is another layer that send it back together to send it back to the initial embedding dimension, and at the end you get exactly the same sizes as initially. And very important is that this position-wise part in the name, that they are applied token by token. So there is no mix of token when after this point. So this is applied to each token separately, like you would apply it to an input of the neural networks that you saw yesterday. So one token is going to pass by here, all in parallel, of course, but there is not going to be mixing. And at the end of that, there is adding, skip connection, and then normalization. And then we finish with this part of this side that we call encoder. And so we can stop here quickly and look at the notebooks. I made, we have here a notebook for attention, and I don't know if we should go in that detail, but maybe quickly I can show you how this looks. And so here we did the same operation. We got the model, tokenize, and the config. We did some encoding of let's tokenize. I put something a bit longer for the plottings. And we got tokens. The tokens we converted in word embeddings, right? The re-embed is, I go back here quickly. So it's a string to tokenization to tokens to embedding table, and then you get a list of embeddings. And this is what we have done in this first part here. And now we have our sentence as a sequence of 15 tokens of size 768. Okay, this is what happens here. And now something that we can have a look is we can compute the cosine similarity. It's not the same attention weights, it's a similarity function, but similar to the attention weights, but not exactly how we can compute it. And when we plot here, we can see the similarity between all the tokens, embeddings in the sentence that we have. And of course, the diagonal, so the highest similarity is a token with itself, that is 1, or embedding with itself, but there are combinations that they have more or less similarity. And this one for us to, it's hard to understand. It's again designed for the machine. And so this is the cosine similarity. This is the same thing that we did with the king and queen. And if we implement a simple attention, is we have our sequences, the sequence, and this BMM means batch matrix multiplication. This is just a matrix multiplication, but for batches of data. But here what we're doing is doing a matrix multiplication of the two sentences, which actually what gives us is all the similar to this, all the combination of dot products. Okay, and we can of these dot products we can do the softmax. Like here. So we have all the dot products. We do softmax in one direction because it's symmetrical. And we do here again this weighted average. Again, I'm sorry about it, but as a matrix multiplication. And we get again the same size of the original sequence, but everything has been mixed up with this weighted average to give context. Okay, and if we plot, we see something similar, but it's rather different. First, we don't have these ones here anymore, because let's say for let, we get all the dot products with the rest of the tokens, and then based on the values that it gives, we do a softmax, and this one, the higher values, it will be probably let with itself, but it has to be it's a scale, so all the whole of them they add to 1, and so on. And this one, so we get some similarity. Again, for us, it's very hard to understand, but there are things that they are found in this way to be similar. Like token, for some reason, has some similarity with notebooks, with examples, and with the tokens tokenized. And I guess maybe because this one are announced, all of them, and they are found relevant in the way that the embeddings they ended up to be. And then the weighted average of token. So before we have the embedding for token, and now it is going to be replaced by a summation of all the other embeddings plus the values that we get here with these colors. It means that notebook, example, ice, let, and token, they are going to be added to this embedding with a lot of weight, whilst this apostrophe, S, and the rest, they are going to be added with very little weight. Okay? And now token, after the attention block, it will have it's not going to be just token, it's going to be token in this sentence. And finally, I won't even stop here, but this is the implementation of the scale.product with the matrices. This one, I just did it in case you're interested, but to use a language model, it's not crucial that you learn how this is implemented. And actually, it's not implemented like this. It's like everything's like in a single vectorial operation. But if you are interested, you can have a look how this is implemented. And now we have exactly the same thing, but now we have these matrices that because we projected, and now this thing, since WQ and WK they are different, this all the combinations of the dot products is not going to be symmetric anymore because we projected to different space. So we get something even stranger, and then the values to do the weighted average are found from here. And having different W's, it will make these weights to be in different places. And thanks to that, we can do the multi-head attention and get different features from different attentions from the same sentence.
If they have the same size of matches,
Yeah.
so how do they train with different starting conditions?
I had exactly the same question, and I got an answer that I don't know that during training some things are done so it doesn't happen. But I was thinking why they don't they are not trained to be the same. But I think it's what you said. I think they start from different random places, and the loss function surface is so complicated that I think that it's very unlikely that they end up all being the same. Maybe they can be similar, some of them. Maybe there is a redundancy. Maybe because the number of attention heads is a hyperparameter. Maybe you have 1 million, and you start reducing, you realize that they don't give too much extra information because probably they are getting very similar. But if you find to a minimum value that they from the, you start decreasing the number of attention heads, and start giving you worse results, you can think, okay, this is a good value that probably all of them, they are different enough. This is what I think, but I don't know if there is something extra involved. Yeah, very good point. Yeah.
Is it the requirement that the projection, smaller space that you project to, that the number of attentions add up to the same dimensionality as the embedding?
No.
Or is that for computational reason? Or?
Yeah, I think it's for practicality, and I don't know for sure the whole idea behind it, but I have read that in general it's done like this, but it's not a requirement. But probably, also maybe for keeping the same load or something, because since these layers are going to be repeated many times, so the output of this output is going to be again done another attention round, another attention round, and another. And invert is 12 times of passing. So I imagine that they want to keep it constant for some reason. But maybe, I don't know if there are more reasons about it. And so this is the attention. I mostly want to show you these plots with the weights. I don't want to spend too much time on I don't want to spend time on the implementation. We know the math and we know the meaning. So outside of this, you get a sequence, same size of sequence and same size of embeddings dimension, and this one is passed to a feed-forward layer, which is this one here, right after and this one I won't run it. So we have the attention here. If you want to do it later, but this attention is implemented exactly as you implemented. Sorry, this feed-forward layer is implemented exactly as you used yesterday. You used the from PyTorch NN module, and here you define there are two linear operations in most of implementations, the common implementations, and there is a new parameter, hidden size. Hidden size is the embedding size, because it's how it's going to, the input is going to be embeddings, and there is an intermediate size, and this one in the first layer is bigger, and then there is so you see here in the forward we evaluate first on the linear one, then it comes yellow activation function, right, and then linear 2, and linear 2 goes from intermediate size to hidden size, and hidden size again is the embedding in dimension. So it projected to a bigger, larger dimension space, those yellow, and projected back to the original dimension. And at the end it has a dropout. And this part is here is the place where I don't know, people think that this is where the memorization of the network occurs. Like, similar analogy that I was putting with the convolutional kernels and the ending part of the convolutional models. So in this case, until here, until this part, so the embeddings and the multi-head attention, I think we can understand it more as extracting features, extracting information from the language, like understanding, adapting the description of the sentence by doing this average and getting information from the context. And then this one, they pass it to a neural network, and this is what is going to train to understand this information. Of course, it's not like that exactly, because already you are training embeddings, you're training the attention matrices, but I think it's a good analogy. And also you can see it, imagine if this is, you create until here, imagine that you have already the W matrices and the embeddings done, and you can use this part here as a description of your sentence. And this one, if you output here, what it's going to give you is like embeddings, but they're going to be contextual embeddings. It's going to be a contextual representation of each embedding. And then you can imagine that this part is, with this fixed part, you're going to train a neural network. Okay, you can see it like that. But in practice, it's not like that. So the whole thing, everything, the embeddings, the Ws, and the feed-forward network are trained at once, and everything is adjusted to find the best, the best parameters that give a good language model. Okay, and yeah, okay, we can go to this part first. Here we see the attention is many times, and we're going to talk about it later, but pretty much we have finished with all the blocks are the same, very similar, you see. It's attention and feed-forwards and normalizations. And so we know already pretty much what's going on in the transformer model, hopefully. And I'm going to talk about the details about the difference between the different blocks that you were asking earlier. But we're going to finally to see this part here that we skipped completely, that is positional encoding. So this position wise feed-forward layer is applied independently to each position, to each embedding in the sequence. So this embedding have been mixed up, but at the end, when you apply this neural network, like they are, like you can see it as batches of a single input. So they are all different, and at this point here, when it comes out of this, if you flip the order of the sentence, there is nothing is going to change. You're going to get exactly the same values, because the weighted average doesn't change because of the order, and this feed-forward layer didn't do anything related to the order. So this is not good, because order is very important in the language. And to give the notion of order to the transformer model, something else is added. You see here it's added to the embeddings, and it's called positional encoding. And positional encoding is a set of vectors that they're going to be added to the tokens to change them a bit, so they can be distinguished by the small shifts that happens to this one, to each of them. And we will see now with this example. So imagine here that this is the embedding space, and the vectors of each word they live there in this embedding. So this is again 768, I think was very high dimensional. This is a small representation, and let's consider this sequence. This is it, okay? And let's say that this is this vector here. It is this one, and is this vector here, and these are the embeddings from the lookup table. So you get a token for this, you look in the embedding table, and you plot it, and it gives you something like that. To give them an information of where in the sentence it is, there are this set of vectors that are positional encodings, and you can see them also as embeddings, but of positions. So there will be one vector that is going to be added always to the word in position 1, another vector that is going to be added to position 2, and so on. And here we can see that. In this, so we have 1, 2, well, 0, 1, 2. So if we add position 0 to this, let's say that the effect that's going to have is that the embedding for this is going to change a little bit down and to the left, and the effect on this one by adding position 1 is going to be to shift it a bit to the right and up, and the position 2 is going to be shifting it down. Okay, so now there is the embeddings have been modified a little bit, and by now that doesn't mean anything. But if we consider this sentence now, is this it? That now is completely different meaning. Is like more like a question, even if it doesn't have the question mark at the end. So now, if we compare before we add position 0 to this, and that shifted like this, and now position 1. And now this is position 1, and adding the vector of position 1 is going to shift it up. Same thing that happened with is, that it was shifted up and to the right. And the same situation will be in this case. Before, when is was in position 1, it was shifted like this by the position 1, but now with position 0, it is shifted a bit down and to the left. And it is the same because it didn't change position. It stays in the same position. And by these smaller shifts, when the model starts seeing many samples, it will start to put together that all these small shifted, they will start recognizing that all these small shifts are the same word. And when it finds that this is here, it's going to be at the beginning of the sentence. And when I find that this is here, it's going to be in the position 1, and so on. And like that, the model starts getting information on what and the relative positions on the sentence. And now by doing switches in the sentence, this is going to be a difference because the embeddings are going to be added by different vectors. Is it clear? Ah, yes.
Position shift, like a training.
Yeah, there are different ways of doing it. One is you get a new position, a new embedding, like for word embedding, so a new lookup table, and now every row is going to be a position. Every column is going to be a position, and so you will add the first embedding with the position 0 of this matrix, and the second for the position 1. So sorry, with the column 1 and so on. And this is going to be trained. It is look for, it's adjusted during training, and then the model, it will find the perfect balance, because the model is going to be training as well embeddings, and it will find the perfect balance, like how much to give to the position and how much to give to the tokens, to the word embedding. So there is a meaningful relation between the words, but also there is a meaningful relation between shifts of words. And in practice, the embedding is never going to be passed like the original embedding to the model. Instead, it's going to be always a shift around the original embedding. And something important is that the position embedding, it cannot, so this radius of shifts, it cannot be too much, because if it is too much, then this is going to start looking like it, and then the model is going to get crazy. But in principle, the model should be able to find out how how this is how to balance them. Sounds crazy, but somehow it works. And also there are positional encodings that are these ones they used to call, they are more called positional embeddings, and the positional encodings are more pre-made, and we're going to see some examples of them now. And yeah, so now we can go to the 5 position encoding, and it's like almost it. We're almost finishing with the model. And so we start with 5. Again, same model. We get the same thing. We do the encoding from this sentence, and again we get a sequence embedding. I have the impression that okay, yeah. And you remember that if we print the model completely, we see these embeddings here in the first block of operations. And now, if we put embeddings, we see that we have position. We have 4 embeddings that we saw before: vocab size times embedding dimension. But now we have position embeddings, and it's 512. And 7 is of same embedding position. And if we look here in config, what is this 512? Oh, in the case, maximum position embeddings. But this is going to be the maximum sequence length that you can pass to the model. And now I hope it makes more sense why it's important also that when you want to apply a model, you want to use BERT, not, let's say you don't want to create a new model, you want to use one that is already pre-made. That this is most of what we're going to do, unless we become model developers. But if we use a tokenizer that is going to convert this less tokenized something in many tokens, then we're going to be using a lot of space of the maximum that we can give to the model with the same information. It would be something good enough that let us tokenize long texts and adjust it to a size like this one, to 512 tokens. So we can access directly the position embedding like here, position embeddings, and it's just a lookup table. We see the weight matrix here. And in this for BERT, they are parameters of the model. They are going to be trained at the same time as the word embeddings. And okay, yeah, these ones I show them. This is the dimension of the embeddings, and this is the maximum length size. And if we so if these are the weights, if we choose the first, we have sequence length 9 tokens in our sentence. If we take the first 9 from the lookup table, first 9 position embeddings, this is going to be the 9 position embeddings that are going to be added to our sequence embedding, to our word embeddings. And so we can plot here and see what happens. So this one, I'm plotting like the position 0, the position 1, the position 2, and together with the token, this is the word embedding for token 1, 2, or 3, just to compare. And we see that the blue is sequence embedding, so it's a word embedding, and it's just some random set of numbers of the size of 768. And then the other one is the other lines that we see, signal, let's say, is the positional embedding. And they are going to be added and form a new shifted version of each embedding, of each word embedding. And there is something pretty cool that is, so in BERT, if we get the, again, cosine similarity between the position embeddings, so just the vectors that give the position, we get a plot like this one, and you see in the middle, so 100 and 100, they are the same, so they are very close, they are the same, but 100 and 101, they are also slightly, you see, it gets very dark and less dark. So the consecutive positions, they are close, right? And the far positions, they are crazy. It's hard for us to understand, but it's less close. So it's not as blue as this. And there is something very curious here that they discuss it in this paper that I put, and that there is this square thing here that is looks very strange. And the thing is that the pre-training objectives, the tasks to pre-train BERT is divided in two different tasks. The first one is a mask language model. Remember, like the cat mask on the a mat, and this trained only with sequences up to 128 or something like that. And then after that, it is further trained with another task that is called next sentence prediction. That is, you give two sentences, and BERT has to output if they can be consecutive or not. You know, if there is a context that they make sense. And they are done with any kind of size up to 512. And then, because of these two divisions with different tasks and different length, this part was learned to look like this, and the rest to look like that. And even cooler is we can see the same plot now with this one is GPT-2. So we're going to get the GPT-2 model, and you see this is kind of small, but if you look at the embedding size, it's 5,000, while BERT was 3,000 something. And the same is the same. As you see, WTE is, I guess it's weights, it's like token embeddings of the tokens, and this one embeddings of the position. And we have the positional embedding here. And we look also the similarity with them, that is also learned. It forms a really cool pattern, oscillatory, and this just happens in the way that it was learned because of the type of model and because of the task. Because remember, BERT is a mass language model, and it's oscillated BERT is a subclass of transformer different as GPT. And the way and GPT is trained in next token prediction, and the way that this was adjusted, the relationship between them, it makes this pattern is pretty interesting. And in this paper here, you can find some discussion. They have different positional embeddings for different models, and they discuss them, why they are different, and it's very interesting. And finally, I want to show you this one, that this is a positional encoding. And there are models like T5 small, that this is a very large transformer. This is a small version of a very large transformer from Google. And if we look to the layers, there is embed token that 3228, and this 3228 is not the number of positions. So this is the vocabulary size. And if you look there is no embedding for position. Instead, it's long. Instead, this model uses a pre-made fixed positional encoding that is based on combining sine and cosines and changing frequencies, and at the end you get, if you plot them, you get something like this. So I'm plotting again So 0, 1, 2, 10, or the different positions. And so the first one is just like a same continuous sign. But then the other one, there is this thing changed here, and then this one changed in this way. And then for the rest, they have like different sub-oscillations here. And they look like that. And you can see them just kind of like barcode shifts that you do to the embedding when you add these vectors to the embeddings. And you may at some point want to show you this plot, because you may see it on what's it called in the internet and be confused. I have been confused on what is the meaning of this, but it's just all the positions they put. This is this plot that I did here, but just compressed to all of them, and it forms this this pattern like this. But this is just the one stack after the other one. And finally, if we look to the similarity, it looks like this. So the consecutive ones and the same, they are very close, but the farther they get, is less. They are a bit more apart. There is some oscillation here, but. And again, this one is kind of interesting to see, but unless you are developing models or positional encodings, this is something you're not going to work with these things in practice. But okay, as a summary, yeah. Now, sorry, I'm going to. So now we understand pretty much how this thing goes. So you get a sentence in text, you make a token. With this token numbers, you use a lookup table and you find embedding vectors. And these embedding vectors, they need information on the position in the sentence, so they are added here. And now these embeddings are isolated. They don't have information on where in the sentence, in which context they are found, and they are passed to the mask, to the attention head, multi-head attention, and this will give a vector, a sequence again, but now every embedding has been replaced for a contextual version of them. And this one goes to a feed-forward layer that is done element by token by token. And at the end, at this point, when it finishes, you obtain exactly the same sequence, but it has been like modified a lot. It has been contextualized, has been projected to a higher space, has activation function applied, and so it has been modified. And this one, many people use it. They can cut this part of the model and use it for some data to create contextual representation of data after they train it on that data. That doesn't have to be language, it can be anything similar to language that they think can be applied. And there are another two layers in this side of the transformer that we can see this one first. This one is another attention head. It looks exactly the same. It's the same operation. But here, this one is a combination between input from this side and input from this side. And this side could be, say again, machine translation, would be a sentence in English, and this could be a sentence in German. And here, what is going to happen is that they are going the sentence in English is going to attend. It's going to look to find for this the important how's it called, the importance of the tokens in the sentence in German. And this is called cross attention because it's done by two different sequences. This one is called self attention because it's done for the same sequence. But it's the same operation. Unless I'm mistaken, I think what changes is that the dot product to get the attention weights is done between the sentence in English and the sentence in German. And then the summary is the adding is through this sentence. Maybe I'm confused with what is what, but the main point is that the attention happens between the two different languages, so the inputs from the two different sides of the transformer model. And the rest is the same. So it's of max here, we already mentioned it. This is the linear layer, you know, the linear layer. And here, this one is called masked multi-head attention. And this one I struggle a bit to explain it. So the idea that you were asking earlier is that when you have a sentence, so when you are training a machine translation, so you're fine tuning for machine translation, for instance, you pass here a sequence in English, and here you pass a sequence in German, and if the German sentence that comes here goes to a layer of multi-head attention exactly as this one, the contextualization is going to do from the whole sequence, right? Because we do an average of all the sequence. But then when you compare the information that comes from English and the information that comes from German, there will be attentions of everything in English with everything contextualized in German. But at the same time, you want this thing to be able to generate words based on the previous words. And you want that it gets information from here, from English, and information from, remember the start token and the first, so a part in the German sentence, and give you new words. But if you train it in such a way that it can see the whole sentence in German, then it's not going to be useful, because if you ask to, you know, it can learn wrong what to predict, because it already has the answer inside of the inputs. No. So I will sit down.
I have a question. Where exactly in this loop does, because for the cross attentions that you said that this is where it finds, like the sentence in English looks for the importance of the tokens by weights in the sentence in German. Is this where the translation from English to German occurs, or is it where the position of the tokens in the sentence in English and German are matched? Like the order of the words in English may be different from the order of the words in German. Then my question is this where the translation from English to German occurs, or is it where it decides the position of the tokens in the sentence in German?
Yeah, I think it's both and none, because the translation kind of happens in. There is not like a single place where the thing happens, where anything happens, because as I mentioned before, like, just to put an analogy, I was telling before that you can see that all this part is feature extraction, and this part is memorization. But at the end, everything is trained at the same time. So this is changing, and this is changing during training. So it's hard to tell what is happening. The only thing that you can tell is that here, if we go back to a couple of slides to this one, in this part here, you will have this sequence. You have two sequences instead of one, and you will have a sequence in English and a sequence of embeddings with their positions and everything, and you will have a sequence of embeddings in German. And when you calculate these attentions here, you are getting dot products between all the elements in this sentence and all the elements of the other sentence. So of English and German. And then you average, I think, over German or over English, but I am a bit confused about it. But the main point is that this one, the model for the first time, get to tell what part of the English is relevant for what was given in German, or what part in German is relevant for English. And then through the rest of the model, it finds out how to translate, what to make with this information. But you cannot tell that something like the translation itself happens in the layer. In this layer, it's just it will do some average of the two languages based on the importance of these words, how important are for this one. And I understand your point that the order maybe it can be confusing, but yeah, it's confusing for us to understand what is happening in the model. Actually, interpretability of these models is just a field, and it's really difficult to understand. But for us, I think the important part is like here, the two languages for the first time they get mixed. I hope it didn't answer your question, but I think at least I give you some insight on why I didn't answer your question. And so going back to the mask multi-head attention, just forget for a second about the word mask, but so I will do something, maybe not too. So this is not really a part of the of anything, but maybe it can help you to understand. So I had it on the. I had it on the notebook and on the slides, and I removed it. So this is not really part. I don't think this happens actually in the model, but let's say you're translating from another language to and you want the translation is the cats. You put something in Spanish, and you want that the model gives you this translation. The cat sat on the mat, and the way you train it is similar to the way that it's evaluated. You put here in the base language, you pass it through all these layers that we know what they do, and here we have an encode representation of the initial language of Spanish, let's say. And now here, when we were using it for production, we were passing, remember, the start token, and then autoregressively will generate the sentence in the final language until it gives end token, okay? But in training, it's a bit different. In training, we have the answer we have already the cat sat on the mat. Well, I forgot the last one, but the cat sat on the mat, and we pass the two sentences. We pass the cat sat on the mat in Spanish, and then we pass it in the target language, that is in English. But if we do the attention, so if we compute the attention here, and we pass, we mix we do weighted average of the whole sentence, then when the model, when it arrives here at this point, it will be comparing the sentence in Spanish, in the base language, and the final sentence with this D. It will have information of the whole sentence. The cat sat on the mat, but on the other hand, you want it that it works in a way that when you pass only the sentence in Spanish, and you pass only the word de, for instance, only with that information, it is capable to give cat. Now, if you train it by giving a de that is actually not de, but instead de plus all the context, because you apply an attention to it, then you are cheating, because in practice, when you use it for modeling, for predicting, you will never pass the whole sentence. You will pass only de, and it won't learn to find the rest of the sentence only by looking at de, because it never saw the word de. It always saw the word de plus a lot of a large context. No? No? No.
Tell me about the first the or the last the.
Okay. No, I cannot do that. I wanted to hide the one part, but it doesn't work like that. Okay, I will give it a last try, and if I don't manage, I will write a letter to you afterwards, and I will try to explain it, or I will send a link to a better explanation. I had problems to understand this a lot. It's part of my struggle to explain is that I learned this not too long ago, and it really was difficult. Okay, if we go back here, so we pass here. This part I think you already got, no? That here, when doing predictions, not training, predictions, you will pass the cat sat on the mat in Spanish, they say, in another language. And here, you won't pass anything. And it will have internally, or you will pass, let's say, the start token, and it will should give you the word de. Because this is translation that is right. Okay? This part you understood? No? And so it gives you de. So, and with this de and the information here of the base language that you don't change, you pass de and you want, and the model should give you cat if it works well. But how, from what it is giving this cat is only from the information that you gave in the base language and the information and this de, and the word de. With these two things, if you pass de and you pass another sentence in a different language, it should give you the word cat. Okay?
But when do you pass the sentence in a different language? Because you said you first pass the, and then you don't pass anything to the right side, right?
No. Yeah. So the whole sentence is on the maybe I think you can write here. Probably not. Probably yes. Going away. Okay. We have time, so this is almost finishing, so I think we can take time to this. And I think it's a very important part. So here, it's a bit big, but it's huge. So here we're writing in Spanish something. Can you see? El gato. Okay, so you have this word in Spanish, this sentence in Spanish, and now you pass it here, right? And then it is going to go all the way here, and here you will have an encoded version of this, because it passed through a lot of transformations, and then you get some thing that the model found as output of this. Is clear? At this point. So this one, this encoded version of the sentence in Spanish, it will come to this part of the model. To this part of the model, it has never seen anything of Spanish. It's just, this is the first part that they see something, so through this line here. So here, you will pass a magic, a specific token that is not a word in English or Spanish, which is, let's say, start. So when you pass start, this start is going to come here to this layer. It's going to come here to this layer, and it's going to interact with this Spanish word in an attention way. And as a result, this is in prediction, so doing predictions, not training. The model should give the word de. Okay? And how the model knows, from what information the model knows to give a de, is only from what was given in English, it's not the information the model has at this point, and the start token. There's no other information the model knows that so it gives the words there.
Well, there's tons of weights in all of that multiplicative entry stuff as well.
Yeah, of course. It's through this. Through this. Okay, but it's not extra information that we gave. It's just we finish with these weights, and okay. So the model knows this. And now, if we want to continue, that probably we want to continue the prediction. We go back here. I mean, it's not we. You have like a program, of course, and we pass now a start and the. And from these two tokens, start and day, plus this thing that is still around, see, still here cached, the model should be able to predict cat. No, cat. Oh, cat. And so it's not going to give like dog, because the information that he knows that from this information, the most probable word in this sentence is going to be cat. Okay? And so on. So, and until you repeat, so you put cat again here, and you repeat until you have the cat sat on the mat. And at the end, it will give a token that it will be like a stop. And that you know now that your program, okay, I will stop. I won't put a stop there. I will stop here, and this is the translation. Now, an important part of this is that when we had only a start and the model was capable of giving cat from these two pieces of information, from the sentence in Spanish and the sentence in and this de. Okay. Now, what happens if when you train it, if you had here a normal attention head? So when you train it and you have a normal attention head, remember that the interaction between the two languages is always here, right? In the cross attention, this one here. If here you had a normal attention, it means that when you're training, you pass both the whole sentence, in English and in Spanish. The cat sat on the mat. And of course, stop. Okay, stop. Then what is going to happen if you have a normal self-attention here is that this de at this point, when it comes out of here, right? It's not going to be de anymore. It's going to be de plus cat, plus mat, and so on. Because this attention layer converted it in a contextual representation. Okay? And now when, this is, okay, during training, right? And now when you do this mixing, that you mix both languages, what the model is seeing, this head here we're seeing for the first time, is not the word de anymore. It's the word de plus cat plus sat for whatever. So then if you train it like that, then when you pass in production to predict, you pass the word de, and the model, probably the model had never seen it, because you always passed a contextual representation of de. You pass de always inside of a sentence. And then it's not going to be capable of give you cat based on that information. Then what is done is to use a different type of attention. It's just the same attention, but there is something, another extra math thing that is applied, and it's called mass self-attention. And what it actually does is that the first word, I think this one didn't help actually. The first word in the token, sorry, in the sentence, after passing this attention, is not going to be contextualized. It's going to be de, because this is what the model needs to learn. Just a word without any context, just left. And the second word, it will be in practice when you pass the cat here, in prediction, what is arriving here is the context of the and cat. And based on the context the and cat plus a sentence, it should give sat. And then this one, cat, is going to be contextualized with the. And sat is going to be contextualized with the cat, and so on. They are always going to be contextualized only to what is to the left of them. This is what the mask self-attention does. And this is only by, it's a trick by, if the attention weights you make the higher triangle 0, then I'm not going to go to the matrix multiplication, but it is going to produce tokens in that way, that only the contextualization is going to be done whatever is on the left. Here, in there's nothing on the left, nothing is going to be done. Or maybe this is valid for start and not for the, but you get the idea. Cat for these two, sat for these two, and so on. I hope at least you have like suspicion of how it works. And again, it took me more time than the time that I have spent here explaining. But that's the idea. The idea is that this attention has to be different, so it allows for afterwards using autoregressive, actually for do an autoregressive training and autoregressive prediction, because if you give context from the right side, then it's just going to affect the model, because the model is never going to work like that. Okay, I'm sorry, I hope we can discuss later, or maybe I can suggest you some videos. And I think it's hard everywhere. And just finally, in the last 10 minutes, we can go through the different transformer architectures. And then in the afternoon, we have a tutorial that somehow has nothing to do with what we have learned today, but I think it's going to be useful. So this picture that we have seen so far is called encoder-decoder. So this part is called encoder, and this one is called decoder. And it's used for tasks, as you have seen already, like machine translation, text summarization. And these are in a category that is called sequence-to-sequence. That is, you give a sequence, like a sentence in one language, and you get a sequence, like a sentence in another language, or a text and a summary. And this is thanks to all this sequence-to-sequence application, is thanks to the mask self-attention that allows for an autoregressive model. And so, okay, yeah, it combines encoder and decoder, and it has 3 different types of attention. Self-attention, cross-attention, and masked self-attention. And examples are BART and T5. T5 was the last one that we saw with it's from Google with the pre-made position encodings. It's a very large model. There is another model that is called encoder only, that it has only this side, but with an ending here. And this is the case of BERT. And similars like Roberta and Mobile BERT, this is what we're going to do in the afternoon. And these ones, they are, since there is no mask self-attention, they are not, you can force it somehow, but they are not autoregressive. They're not suited for autoregressive modeling. And this one, what it's going to do is that you're going to pass it, to pass a text, and it's going to give you like small numerical representations or things like that. That could be like a classification of text, like you know, giving a review, giving you this is a 1, 2, 3, 4, 5 stars, or sentiment classification, sad, angry, whatever. And the question and answer that we're going to explain later in large extent. And this one, so BERT, this B, it comes from bidirectional. And this bidirectional comes from, it's the opposite of the mask self-attention. So the context comes from both sides. And I think it's called bidirectional encoder because it's an encoder-only model. And I don't remember the R, what is it? I don't remember what is it, but the B is bidirectional. And everything, all the features come because of the lack of mask self-attention here. And the last one is, of course, decoder only. And decoder is also for sequence to sequence because of this auto-regressive nature. And this one you can use it for text summarization, for instance, or something that you give a prompt and it just continue building from it. It's just generating next token always. And again, this is because of the mass self-attention. And you can do translation with this one, and it would work different because it doesn't have both sides. But the idea would be like you give a big prompt, like El Gato or whatever in Spanish, and then something like translate, some order, and then it will start generating, you train it to generate in a different language. So it can be tuned for different tasks, but in total it's a sequence-to-sequence model, and this is what GPT is. So GPT is a decoder-only model. So you can write your prompts, and then it will generate from what you wrote. And that is it for the transformer architecture. In the afternoon, we are going to do something in practice with it, and we're going to see that Hugging Face has made very easy to work with transformer models, and most of the work that we have to do has to be with the dataset. And I won't explain it now, just to let you rest. And I think, yeah, this is fine. And I put here this kind of a pun, but thank you for your attention, because attention. Not put in red, but. And yeah, do you have any questions? Yeah.
I have a question that actually relates to one of the last slides. So, with these models, I have a good understanding of how translation works. So basically, the model learns the structure of text, and then kind of straightforward to go from one language to another.
Mm-hmm.
But in like a GPT case, if I give a prompt like make a summary of this text, can you give me an intuition of how that is possible?
Yeah, I think GPT is trained in different. It starts pre-trained with next token predictions. You give, a context, and it will give you what is next, and that can give you already an idea of how this is going to work, because it could be trained that when you find that you said give me a summarization, now they know what summarization is, and it knows to find, okay, this after summarization, then what comes is probably the text that I'm going to summarize. And just from this information, the most likely tokens are going to be the tokens of your summary. But so it starts training like that, but afterwards it is fine-tuned with specific things like that. It will see many examples like exactly like that. Give me summary of this, and they will compare with the summary, and eventually we'll learn that when you see a prompt like give me a summary, and then it is something after that, you will know, okay, this is the order, and this is what I have to summarize. And same for translate the following sentence. So the Bertha has this tokenization is very byte level, so there are not really characters, it's just bytes. So he can tokenize everything. It doesn't matter with the language, it's just tokenize it with the same tokenizer. And then as a result, it will be translated many times it will train many times in examples that this translate this sentence, and you will write something in a different language, and he will understand now that what the next tokens, the next most probably tokens are a translation of this part of the prompt. Is that what the question, or is more technical?
No, more or less. My question was not on the prompt itself, was rather like on the task of make a summary. Because if as a person you would have to make a summary, you would have to think about what is most important in a text.
Yeah.
And I was kind of trying to get an intuition of how the model can make a summary.
Yeah, I think for the model is like given this context, what you want to summarize, the model is trained to find out what are the most probable tokens auto-regressively, like it gives one and then the next one, the next one, next one. And so it's not based like he read everything, it's based on whatever is there, what it would be more probable. So there is no going back. Eh?
Use the attention model to extract the most important parts.
Yeah, exactly. Yeah.
The same question. When I say to ChatGPT, explain how a combustion engine works, it's seen the phrase explain how, and then it just looks on Wikipedia for combustion engine.
No.
But it doesn't know how a combustion engine works. So when I say explain how a combustion engine works, it then has to look up that information from somewhere. So it has these chemical models embedded in higher level.
Yeah, it could be like here, for instance, in these parts. It has the other day. So I'm talking a lot about that guy, but I saw another. I also put the link or these YouTube videos of the same person that I mentioned before, and he was talking. It was called large language models something, and he didn't mention the word transformer in the whole presentation or machine learning. He was talking about it as introduce them as a way of encoding internet information in the weights and accessing them through prompts. And how that happens inside is a bit of a black box. So inside of the model, there is encoded somehow, if he saw it, of course, how that combustion engine works. And when he sees this prompt of how this works, it will access this part of the information, same like, I guess, the brain or something. And it will make that the more probable tokens are going to be related to that area of their memory or whatever. Maybe
The words combustion and engine will frequently appear together, so it knows to put those together because.
yeah, of course, yeah.
And it knows that cylinders and that, carburetors and things are involved, with related words.
Yeah.
But then for it to regurgitate out an explanation of how it works, it's just meant. Does it not? It doesn't have any. I don't know what I'm trying to ask. What transformer? Is it still? I mean, is it basically? It's just that one transformer model, or is that embedded in lots and lots and lots of other stuff?
Well, this one. So you see here, there is n. So this thing is repeated many times. So there are like many blocks of like. Let's say that this is maybe the memory. Now I'm being a bit exaggerated. So there will be many weights, parameters, and all these weights there, this is just information that it saw during pre-training, and it's encoded there. It's half of the internet put, well, not half, but a big part of the internet put there, encoded in weights, and who knows how that is accessed actually, for the model. But yeah, I think it's just that. There is nothing else. It's the same that you saw yesterday with the generation of images. There is no the information of the images, and it is just encoded there somehow. And by doing the prompts, you access them. And not always works. Sometimes he was showing like things. He would put in an example. I think it's a classic example. Like he would say, "What's the name of the model of Tom Cruise?" And he would give the name of that person. And right after, he would ask, "Who is the son of that person?" I don't know. And it is the information is there, and through the right tokens is a way of curing this information, and it's complicated. The interpretability of these models, I don't know anything about it, but it's a complicated field, and it's a bit of a black box in many cases. And he also was mentioning it that one of the tasks, future tasks, is to, instead of, as you said, just give the prompt and then just by probability just generate. He was saying something like it would be one of the things now is to try to find out, to tell him, sorry, him is in Spanish, is masculine, but to tell the model, do this task. So give me how this combustion engine works, but take half an hour there. Just go through there and find different channels, and I will come back later. And this would be a different way of accessing the information that is not like just started generating immediately. But this is how it is. Questions? Yeah.
Could this transformer also be used for predicting the next steps of a video instead of the
Yeah.
word
Yeah, like 2 weeks ago or so, while I was preparing for this, OpenAI made an announcement of video generation. Yes, SOTA or something, no? SOTA. And they have I saw somewhere, they have a diagram where they show the videos, and they basically tokenize the frames, and they use these frames, not frames, like patches of frame, and they applied exactly the same attention things between these patches, and afterwards they generate most probable patches, and they form images, but actually through time. And actually they can use the same model to generate images and actually videos. And also this is not only because image and somehow and language, they have some connection in that there is some correlation between, it's not like random signals, one after the other one. So the language, they have some structure, and same for the images. Otherwise, it's just noise. And the fact that there is this structure, I think the similar techniques can be applied for both of them. And also, they use it for, there are tokens to generate like instructions to give to another program to look for information in the internet. Like with GPT-4, for instance, you can tell him, could you find me this in the internet? And from this token, he knows, from this sentence, he knows what token to generate, to give it to another program that is going to it knows how to, with some information, he knows how to automatically go and click somewhere in the internet. And yeah, he actually was showing how a language model could be like the kernel of a lot of operations. Like you talk to it, and then it will go and interact with a browser in the internet, and will find things for you, and will interact with the machine, and with I don't know, start some process and whatever. So it's not only language; it's really more general than just languages. Apparently, anything that you can mass tokenize properly, you can apply with some success or not, but transformers. And just before we go to launch, because it's a bit late now, these probabilities in ChatGPT, so you have the softmax, but you know that you ask the same question today and the same question tomorrow, and it's not the same answer. It's a different. So he's not going to do argmax and give you the more likely word. It will do, this is a softmax at the end, and the model itself is a probability distribution. And so there will be some randomness in sampling what are going to be, sampling for that distribution. So that's how there are always different paths, depending how the sampling goes. Okay, so maybe we go for lunch now, because it's 12:06, and we come back, we can discuss more, and we can see an example of how this thing works. Okay. So we were discussing at the end about how much information these models they have. So this general, these models that they can do so many things, like ChatGPT, they are really large model of billions of parameters, and sometimes hundreds of billions of parameters. And yesterday, the large neural networks that you saw were in the order of 100 million. And so this one is 10,000 more parameters, 1,000 more parameters, 1,000 times more parameters than what you saw yesterday. So they need this really amount of parameters in order to encode so much information from all the text that they see during pre-training. So now in the example that we're going to see in the afternoon, we are going to do fine-tuning of a model called Mobile BERT, and it's a version of a not too large transformer, but it's a version of reduced size version of that transformer. And so we can go to BERT, the notebook. BERT squad. And we can start by having a look to the data set that we're going to work with. And yeah, so the problem that we're going to work now in the afternoon is a task that is called text extraction. I talk a bit about it, but just a refresher. And in particular, this is going to be a question and answer text extraction. And the idea is that we have a text that, a data set that has many texts, and every sample is going to be a text that in the data set they call it context. It's a big paragraph, and there is a question associated to that paragraph, and the answer of that question is inside of the paragraph. And we're going to train the model to tell us from here to here in the paragraph is the answer. So if you remember from the morning, the type of model that we're going to use for that is an encoder only. An encoder is the one that you give full sentences, and since it doesn't have mask attention, it takes bidirectional information of the sentence, and it can produce numbers from it. And these numbers can be a classification in different, like sentiment analysis, like happy, sad, aggressive. Or in this case, it's going to be two numbers that are going to be the position, so the token in the string of tokens, the position where the answer starts and where the answer finishes. And yeah, so we're going to start by having a look to the data set, and I can explain you a bit about how you work with Hugging Face. And then afterwards, we're going to do the training, which I don't know if you can actually finish it, because it takes like a half an hour, and I don't know if you want to spend half an hour training that, unless you have something else to do. But it's going to occupy the GPU, so probably you cannot do anything else in that time. But I can show you how to train. You can show some steps and see how the loss goes down. And afterwards, I saved already a model that is already trained, and we can try it and see how the evaluation works. And we're going to print some answers in a set that the model hasn't been trained. And okay, so if we go inside BERT, we can start with the notebook 0, squad BERT understanding, something like that. So this one here, understanding the data. And so here we're going to use one from, also data sets is also part of Hugging Face, and we haven't seen it so far, but it's a collection of data sets. And this rich pretty is just to print pretty, because we're going to print many dictionaries, and I think it's nicer to have them with indentation. But this has nothing to do with the transformers. So auto-tokenizer, you already know. It takes the tokenizer from the information of the checkpoint that you can download from Hugging Face. And we're going to start with getting the data set. And this squad stands for the Stanford question answering data set. And we're going to see how it is composed. So if we print the data set, we have all these items, and they are divided in train and validation. Train is 87,000, and validation is 10,000. So we're going to train in this data and test in this data. And yeah, we can actually print and go what these things are, how they look like. And so here is a sample of the data, each of these green things. There is some ID, that is one we're not going to work with them. And there's a title, we're also not going to use it. And there is a context, which is this paragraph. It's not too long, but it's not a sentence, it's some a paragraph. And the question, in this case, is to whom did the Virgin Mary allegedly appear in 1858 in Lourdes, France? And then there is the answer here, Saint Bernadette Soubirous, and answer start 512. This means that in the sentence, but the sentence in text, not in token, if you look for the 515 character, then it's going to have Saint Bernadette there. It's very hard to find now, but we will see later. Okay? Is it clear? So the samples are like that. The text, the context where we care, the question, and the answer, and the position where the answer starts. And so validation is exactly the same. Something about the Super Bowl, and then yeah, we can put some examples here and print them. I just put this so you see the things that you can do with the data set. So we have this is amount of training samples, and for each title, which is like a topic, there are different questions. This is a topic and a context, and they have different questions. So the context is repeated many times. You see that the titles is 10,000. This means that the context is 10,000. And this is in validation, and this is in train. And validation also for TA, the title. No, there is something strange there. Validate title, validation title, validation title. Okay, sorry, I'm seeing here the unique. So this is all the times the title appears, and this is the unique amount of titles, 48. Sorry. And here we see this again, just for you to afterwards play with different things with the data set. This one is about the Alps. The question how long has taken for the Alps to form, and the answer is over 10 of million years, an answer starting for 75. And I think for 75, maybe at the end, it has to be somewhere, I just don't see it. But this over tens of millions years is somewhere in the text, okay? And so this is the data set. And remember, the first thing that we do with the data set is tokenize it. And in this case, we're going to use a checkpoint called Google Mobile Bet Uncased. And this is going to have the pre-trained checkpoint of the model. And I think this one, I'm sorry, I think I skipped to which task this has been trained on which data, but I imagine it has to be masked language modeling, but I don't remember now. So we get the tokenizer from the checkpoint. And here I think we printed in the morning for BERT. This one is very similar to the BERT. I don't know if it has a difference at all. If we tokenize something, we print here tokenizer. So this is the tokens, and let's see quickly how it printed it. It looks pretty much the same that we saw in the morning. Remember that token was divided like this with the sharp eyes, and with the callback. And here, when you do tokenizer directly, not tokenizer convert or tokenizer encode, but directly, it will give you all these three things. And this is very convenient because you can use it for, this is already the input of the model where the tokenizer was used. And this, it's a freebie that Hugging Face gives. And we have this already done. We're going to go one by one what this is the tokens, but these two, we're going to see what they are. And it does something also convenient for this task of question and answering. That now we put two sentences that in our application, one is going to be the question and the other one is going to be the paragraph, the context. And here he divides in zeros the tokens that belong here, that belongs to the first sentence, in this case the question, and with ones that belongs to the answer. And like that, this is used internally in the model during training, okay? And this is going to be the input of the model, or part of the input of the model, okay? I'm going to explain what these things, how this thing works. But okay, you know this one. What is called token types? One is going to be belonging to the first sentence, and the other one to the second sentence. And attention mask. Just to we will repeat it later, but just to tell you here to not leave you hanging. These are all of them. You see, they are one, but we are going to make something so that they all have the same length. So remember that the transformer model has a maximum length that it takes, and you have to give this length always in all the samples. So if the sentence is not long enough, you pad it with a padding token, which in this case I think is going to be pad. And then this attention mask is going to be 1 for what is text and 0 for what is padding. Okay, we're going to see later. And so now we're going to work obviously with this data, and here the number of the length of this string is not associated at all with this with the length of this of the sequence of tokens, right? But however, the position in the data set, the position where the token starts, this one, is thought to be is meant to be on the text. So we have to transform. So we already tokenized, but we also have to transform this position from position in the text to positions in the sequence of tokens. And this is what we're going to do with this function here, tokenize data set. We can discuss later if you want, but I won't show the details now. But once we apply this transformation to the data, then all these tokens are going to be padded to the maximum length, and we are going to actually cut the length to the 300 instead of 512, just to make it, I think the training is slightly faster. And what else? And we are going to transform the answer start to position where it starts in the token instead of in the string sequence. So this was you're going to see how this is applied, and also there are some sentences, some cases where the answer starts and finishes after the part that we have cropped. This one we're going to take them out. We're going to filter them out of the data set. So first we're going to, so this is the data set, again printing here. And the first thing that we're going to use is the utility filter. And we're going to pass this function here that is going to be true if the size of the part that we truncated, so we truncated here in 300 tokens, contains the answer, and it's going to return nothing, or you can also put false to the ones that are outside of to the answers to the context that have the answer outside of our truncation limit, and this one they are going to be taken out of the data set. This is what filtering means. So if we run here, it will crash. I didn't run this one. And so here we can put multiple workers, and it's going to do it quickly. And now you see that here is 87,599 and 87,289. Some of the samples have been taken out. Same for the validation. Around 60 have been taken out. And at this point, we still have the same thing in text, and we're going to use the other transformation in a new so in this filter data set with a map instead of a filter, and this one is going to do the tokenization, to do the transform from the position to position in tokens, and it's going to delete the old old columns with text, and it's going to replace it for the new columns that come from here, and some other things that we added you will see now. So now if we look at the new data set, so it has the same amount of samples as the filtered ones, but it has different columns. And now we have input IDs, which is the tokens, token type IDs, what is question and what is paragraph, attention mask, what is padding and what is text, token start and token end of the answer. And these three, we introduce it here because of the tokenizer produce them. So we use tokenizer here. And so we get already a dictionary with these three samples. And finally, we add these two once we transform the positions and we find the position in the token. And this, how it works is here you put the final dictionary that you want, and this is just going to add, it's going to go sample by sample, and it's going to replace each sample, but whatever you're putting here, or add it. Add it is if you don't set remove columns, and I put the names of the ones to remove. And in this case that we did put remove, it's going to replace them. And now we have the new columns that we get. Okay? And so we can have a look to the training. So everything looks like this now. These zeros are padding, and this zeros is masking of the question and the text. And attention mask, it tells the text is until here. From here there, make zero everything and don't do attention with this padding. Attention means attention block. Okay, and yeah. So these three things these five columns that we got here, we are using as input of the model. And in the next notebook, so we can see the shapes. All of them there are 300 because we truncated in 300 and padded. So truncated was longer and padded was shorter. And yeah, I just repeated a lot many things here for you to play when you play with it. Here decoded, you see all these zeros become a token that is this sep, it's the end of the sentence. But now there is a lot of pad after this sep. Okay. And similar to attention masks. So attention masks, you can evaluate the input IDS in the attention mask, and you say when it's equal to 1, and it's going to give you just the paragraph without the padding. Same thing you can do to separate the question and the answer with the token type IDS. And sorry. And then these two, they are just which token is the first one of the answer and which one is the last one. And yeah, and this is it. So now I will explain you quickly the first notebook. So you prefer to make a pause and go through the data set alone, or we go directly to the second notebook? Okay, so in the second notebook, I have it run already because I was saving some data sets. Okay, this one is the most relevant for the transformer part, and I think it's going to be a bit disappointing because, again, Hugging Face has made everything too easy. But when you start working with it, you will be happy that it's so easy. So we know this part already. Tokenizer, we get it from the auto tokenizer from the checkpoint. Same from the model. So in this case, we loaded mobile BERT for question and answering. And from pre-training, now we have the model. We can print it here. And so an important thing is, like, it says here, some weights of mobile BERT for question and answering were not initialized from the model checkpoint at Google. Do you know what that could be? So this is because this checkpoint, we're getting it from a pre-trained model. And actually we can do that. We can, I don't know how it's called, but probably is mobile BERT for no. Pre-training. Okay, so there are many different versions of the modeling. Okay, mobile BERT for masked LM. This one could be the one of pre-training, for instance. So there's a bit deviation from the notebook, but let's get this one here. I call it Max Language Modeling, MLM. We are going to do mobile from pre-train. I don't know if this is the one that is used for pre-training. But okay, so you see this one didn't say anything, that some of the weights were not initialized. I think this one is probably because this is the one that was used for the pre-training. And if you print it, you see all the layers, and at the end, the last layer, the last one in particular, this is vocabulary size, remember from the morning. And this is a layer that is going to be passed to a softmax to predict which is the most probable word. Okay, next token. Sorry, next token, no, sorry, mask token. But if we visualize this one, you see all this part is going to be the same, but here the last layer is out features too. And this one is for question and answering, because it's to give you the beginning and the last positions where the answer is. And what's happened is that the model was pre-trained, this model, with this is called task-specific heads. It's the last layers. And afterwards they cut it, and they, let me see. So you see there is this feed-forward network output, and then the rest, all this part was cut out and was replaced by this one. And now with this new task head that is for question and answering, for say where the positions are, then the model is going to be fine-tuned for the Q&A. Okay, and that's why here is complaining that some of the weights were not initialized, and this is because these ones it couldn't get it from the pre-training checkpoint. Is it clear? Okay, so we are here. Squad is the same as we saw before, and here we define exactly the same mappings and filters, and we do this, and now we filter the answers that are too far in the sentence, and here we tokenize and convert the proper positions of the answers. And the good thing of one of the good things of these data sets from Hugging Face is that you can put it directly in a train data loader of PyTorch. You remember from the other day? So data loader, you load it from Torch Utils data loader. And this one is, you can make an iterator directly. I lost it here. And we can do one for training, and we'll put the batch size and the workers, and we can do one for evaluation. But evaluation, we're going to use it in a different notebook, so I marked it, commented it here. So Torch batch size 50. These models in general, they tend to go well with large batch sizes. And this one I will show you now afterwards. I choose this 50 because it was the maximum batch size that I could put without filling all the memory of the GPU. And we're going to check afterwards that. And so we copy to the device. So now it's in device, and we set it as train. And remember, from here, you cannot see it here, but there are dropouts and layers that are train or evaluation independent. So it's important to put train here. When I was preparing this one, I forgot, and it took me some time to find out what was the problem. And we get an optimizer. This learning rate here, remember, is an hyperparameter, and they tend to be, for this kind of model, around 10 to the minus 5, 10 to the minus 4. This one I got it from an example many years ago, but I asked also ChatGPT I explained I'm doing this fine tuning for question and answering with Squad with mobile BERT. What learning rate do you recommend? And he said, okay, these ones are between minus 10 to the minus 4, 10 to the minus 5, something like that. And I tried it, and it worked fine. And here we have the training. The training is the same of like normal PyTorch. Here we have epochs, and we here iterate over the train data loader. But the Hugging Face does something differently. It kind of decorates with the stuff the model. It's not just the model directly. We already saw these inputs that it has that are specific for the mobile BERT for question and answering. Maybe if you have mobile BERT for mass token, mass language model, it's going to be a different inputs. But so it decorates, so you pass already these are the inputs the inputs, and these two will be like the two outputs to compare to what the model predicts, start and end position. But the loss function, here you see that we didn't select one. The loss function is already one of the outputs of the model, and Hugging Face, it puts it directly inside of the model. So output 0 is going to be the loss. And in this case, the loss is cross entropy. And you can see, I have to check. I got a bit confused. I was thinking in the mass language model is cross entropy, and predicting which token is sort of a classification task, because you have a softmax, and the classes are going to be the different possibilities of token. And we'll say it doesn't make too much sense, like what is the class of this sentence, the next token. But the logic is kind of similar. It will give you the next token, which one is going to be in a probability distribution. Here I have to recheck. I'm sorry. Let me recheck afterwards what is the loss, but it's already inside of the model. But the rest is the same. So we have here 0 grad to make the automatic differentiation restart the operations recording. We get the loss, and then we do loss backward, and then optimizer step to move in the update the weights. And we can run here a few I think we can put it a bit faster to see. Okay, it went down. Okay, I will keep it in 5, smaller. And afterwards, once the model is trained, it takes like a half an hour or so. You can save the model, and you can use it later for predicting. Okay, and yeah, actually I can show you that the last one. The last one is kind of easy, and I was going to stop here, but well, we can discuss this one quickly before I give you time. Do you have any questions about this notebook, about the task? No questions or no understand? Don't understand? Don't understand? Please, come on. Generate the next token. Say something. Okay, I will go to the next one. I will give you time, and then I can pass by the tables if you need me, and otherwise we can discuss more. So the next one, we have already a safe checkpoint. So we're going to load from the same checkpoint from Hugging Face, because from that we need to get the tokenizer, and so we cannot load directly from the checkpoint that we did. Or at least I didn't try. I assume that you can't. We do the same filtering of the data, although we could have done it directly with the... Okay, yeah, my mistake, I'm doing it here to the train, but this part we don't care right now because it's just a train. So we do it to the data loader. Sorry, what did I do here? I'm sorry, sorry, I made a mistake here. I will fix it afterwards. No, sorry, no, I got confused. It's fine, everything's fine. So we filter and we transform the data set. So for a second that we were doing it only on the training part. And now we're going to use only the evaluation data loader, just evaluation training set. And for evaluation in general, you don't care for shuffling, but I'm going to put shuffling because here what we're going to do is to print the results and see them ourselves. So just to always print different shuffles. And here again, it's very important to put model eval, and this is going to turn off the dropouts. And if you don't do it for the same input, you will get always random wrong questions all the time. Also happened to me. And so I put here an example that I pre-trained, but only with one epoch, so it's not too good. But we can run the evaluation. So here we're going through the data loader. It's giving a batch of 10. We evaluate the model. And now for evaluation, we don't need to pass the start and ending positions, because this is what we're going to predict. So we pass only these 3. And the prediction, we get them from the output, and the output has already something prepared for that. Output.start logits and output.end logits. This one we pass it to a softmax, and it's going to give us the probability distribution of the tokens. And afterwards, this is by batch. We're going to iterate over the batches. And to the softmax that we got here, we're going to do an argmax. So we're going to get what is the maximum probability token, so the most likely token. And we are going to transform the tokenizer, so the position from the tokenizer back to the text. And this is what this thing is doing. And we're going to print 10 answers, and we're going to see, so here I'm printing the paragraph with the question. And so here I have robot, I call robot the model, and reference is from the data set. Here it got it very well, so it's asking how many schools of medicine were recognized in China. This one, it didn't take it. I don't know if no, it's here. So this one it wasn't capable to find it, but maybe with another epoch it will be able to do it. This one is percentage and so on. This one is wrong, and so on. So there are, in general, so when there are benchmarks, and this is not like a guy like me going through the answers and checking which one is wrong. So there are metrics. I just kept them because already we have talked too much. But there are metrics to compare different sequences and check how well something that was predicted compares to a reference. And there is the blue and rouge metric that they are very famous for that. And they're using in benchmarks to automatically, it gives like I think a number in percentage, and it gives to kind of a proxy of a human. It's not really accurate, but to understand if a model, to rank different models and things like that automatically. I think, now, from now to 3, or 10 to 3 or so, to do some conclusions, you can work on this, or if you prefer to work something else in of the course, is fine. But we can keep discussing, and I give you time.
Sure that the start position is before the end position, then I would modify the loss function.
No, sorry, I don't understand.
The start position of the answer obviously has to be before the end position.
Yeah.
But we didn't embed that. We just
No. Actually, if I can show you quickly here.
The start is always before the end.
No, that is not part of the model. The model is there is nothing. Because in the model itself, there is no limits. It will give 2 numbers at the end of this. Instead of 1, it has 2. and there is no, you can give one or another, doesn't matter. And actually, if you do like this, and you reset the kernel, sorry. If you start with the model, and now this time I am not going to get the checkpoint that I saved. I shouldn't have done that. You will see that I can print them, that they can be whatever. There is no restriction. Other questions in the meanwhile?
Yeah, I guess the follow-up would be like, is there a way to force which constraint into the model? As by starting.
I imagine that probably somehow you can train it with some information like that, but now I cannot think about it. But to me, it's not clear if this is what you want, actually. Because, I don't know, I think you wanted to understand the text and be able to generalize. And I don't know if putting this kind of restriction is going to affect the understanding of the text by paying at, having to learn another kind of behavior that is not just understanding the text. You know what I mean? This is what I think, but maybe they do something, yeah.
But one of the answers had no answer. What does that mean?
It can be that it is completely wrong, that the things are that they are shifted, or that they went outside of the sentence, or it gave 0. Or, yeah, we can print it actually and see. So you will.
No, I just wanted to say that if you interpret the outputs as beginning and length, there wouldn't be. Like this would enforce it, basically.
Yeah, exactly. Yeah, that makes sense. Yeah, very nice. Wait. No. Yeah. No, because I'm thinking like this, because here, before I got a bit confused, what is this? What is the loss function? And I wrote it was the cross entropy. Remember, the cross entropy is what you use for classification. And here, I don't know, at least with interpretation of the model, this means that you are training to give a probability. I think it's going to be the same. One is going to be the probability of the. Yeah, it's going to be the same. The probability of where in this 300 tokens, where is it? And the other one, the probability of how long. Yeah, the same. So here we print. Let me print the model. So before the robot, I can put these two. No. Wait. How is it called? Start. Start. End. Well, they tend to be not too bad. But this one, for instance, you see, this is the model without pre-training. And this is BBC 1, this is BBC 3. So without pre-training, not without fine-tuning. This model is pre-trained, and probably he can do something. And you see here that something is working, but it doesn't give as good answers as when you fine-tune it. Or actually, it does. Actually, I think what I did, I think I was distracted talking to you, and I loaded. Yeah, sorry, I loaded the. Okay, but well, I think this is one of these cases that it didn't show an answer. Probably it's this one. This one here, 101 to 69, and it's blank. I think it gets it wrong. Yeah, but I think that Yeah, it would be interesting to see how it, because this case will never, it will be always enforced if you put length and position. Interesting. Okay, other questions? Okay, now, yeah, this again, you have time to work with these two notebooks. I recommend you to, there are no exercises, but I recommend you to first to try to understand the data set and try to understand these masks, how they work, because anything that you do with Hugging Face, it will have pretty much the same structure. And then afterwards, you can move to the model, to the training, and see how things are done. And if you have questions, yeah, I can discuss with you. And so, just before I forget, normally we send a survey about the course. That is very important for us if you give like good feedback of things that can be improved. And mostly because this was the first time we do this course, and it's not like you have been the test group, but you know, for the next students, I think it would be nice if we got some tips from you and we can improve it if we keep doing it next year, or I don't know, it's not decided, but so we would appreciate if you can do the surveys and give good feedbacks. I mean, good feedbacks, not good things. I mean, like good tips and criticism. And so that, and the rest, I don't know, Rocco, would you like to add something as final words or something in particular that we should remind? No, yes, just for us, I think, yeah, it was very nice that to have the opportunity to have you here, and I hope the course was it helped you in something, and you can get started now easier now that you come back to your work, and you can use these kind of things that we learn. Okay, thanks a lot.